Hello, I'm Sheila Hayter, President of ASHRAE. Welcome to today's webcast. The latest advances in refrigerant technology and global regulations require that HVAC systems adapt accordingly. During this 2-hour broadcast, you will learn how the selection of refrigerants for Unitary products has evolved and the key characteristics for selecting refrigerants for specific HVAC systems. Today's presenters will discuss the future of low GWP refrigerants, refrigerant retrofit opportunities across systems, and the challenges designers face when working with flammable refrigerants. Thank you for joining us today. I look forward to hearing from our presenters and also from you, the viewers, during the question and answer portion of the webcast. Let's get started.
Welcome to ASHRAE's 2019 webcast, The Future of Refrigerants in Unitary and VRF Systems, brought to you by the Chapter Technology Transfer Committee. We'd also like to thank two sponsors for their support of this webcast, Arkema and Mitsubishi Electric. Before we get going, we want to say a special thank you to ASHRAE President Sheila Hayter for taking the time today to welcome us to the program. I'm your host, Jennifer Gladstone. On behalf of ASHRAE, I'd like to welcome all of our viewers. We thank you for joining us. ASHRAE is a global society advancing human well-being through sustainable technology for the built environment. The society and its members focus on building systems, energy efficiency, indoor air quality, refrigeration, and sustainability within the industry. Our vision is to be the global leader, the foremost source of technical and educational information, and the primary provider of opportunity for professional growth in the arts and sciences of heating, ventilating, air conditioning, and refrigerating. For more information about ASHRAE, visit ashrae.org. Now let's meet our panel for today's webcast. Doug Tucker is the Director of Industry and Government Relations at Mitsubishi Electric US in Suwanee, Georgia. In this role, he represents the interests of Mitsubishi Electric with federal, state, and local governmental organizations, with industry trade groups and regulatory bodies, and with energy efficiency advocacy groups. He's a 35-year veteran in the field of standards development, conformity assessment, and regulatory policy of HVAC and R equipment, with a specific focus on safety and energy efficiency. Welcome, Doug.
Thank you.
Sarah Kim is a scientist working on next-generation low GWP refrigerant development. She's been with the Arkema Fluorochemicals Research and Development Department for 5 years as project leader of HVAC and R applications, focusing on the evaluation of refrigerant performance, chemistry, and safety aspects. Sarah, thanks for joining us today.
Thanks for having me.
And Steve Kujak is the director of the Next Generation Refrigerant Research at Ingersoll Rand Train, where he leads a cross-function team of technologists working on low global warming refrigerant technologies. Steve has spent over 26 years being involved in numerous technology and product development projects involving development of new refrigerants, lubricants, compatibility of system materials, and environmental sustainability initiatives. Steve has been an author or co-author on more than 30 publications related to refrigerants and has 8 patents related to HVAC products, including a number of refrigerant composition patents related to R410A alternatives. Steve, it's great to have you on the program today.
Thanks, Jennifer.
This is what's coming up in part 1 of our webcast. Doug will give us a brief look at global regulatory issues, after which our panel will have a roundtable discussion. Sarah will walk us through Unitary HVAC market evolution and global trends. Steve will introduce us to key characteristics of today's Unitary and VRF refrigerants, and we'll hear from you, our viewing audience, in our first question and answer segment. Now, Doug Tucker will begin today's program with an overview of the driving factors in worldwide refrigerant regulation and policy. Doug?
Thank you. Refrigerants have evolved over the past several decades to address changing requirements for safety, performance, and energy efficiency. More recently, certain classes of chemicals were found to have a damaging effect on our environment. This knowledge has resulted in transitions in the types of refrigerants used in air conditioning equipment. First, because chlorine in the stratosphere is known to be one of the primary causes of the depletion of the ozone layer that shields the Earth from harmful radiation, Chlorofluorocarbon, or CFC refrigerants, such as R12, were phased out under an international treaty known as the Montreal Protocol. This treaty, enacted in 1989, established the metric of ozone depleting potential, or ODP, to quantify the effect of a refrigerant on ozone when released in the atmosphere. The subsequent use of hydrochlorofluorocarbon, or HCFC refrigerants, such as R22, was understood to be a short-term solution. Although HCFCs have a lower ODP, they are not near zero, which was the ultimate goal. The introduction of hydrofluorocarbon refrigerants, or HFCs, began in the 1990s. HFCs then became the primary substitute for R22 in Unitary and VRF systems when the use of HCFCs in new equipment was prohibited in 2010. This transition introduced non-flammable, low-toxicity refrigerants with a zero ODP. We are now facing another transition in North America, one that is already well underway in Asia, Europe, and Australia. What is driving yet another refrigerant transition? Although HFCs have zero ODP, they are considered a potent greenhouse gas. The global warming potential, or GWP, is a measure of how much infrared energy the emissions of a gas will absorb relative to that of carbon dioxide. The larger the GWP, the more that a given gas traps heat compared to CO2. For reference, the GWP of R410A, the most common refrigerant for Unitary and VRF systems, is 2088. Even though HFCs represent a very small fraction of global warming gases in the atmosphere, they are growing and could potentially contribute up to a quarter of the increase in global temperatures projected by the end of the century. Air conditioning systems also affect the environment through indirect CO2 emissions associated with the energy used operating the systems. Since direct emissions from leaks and unintentional venting account for less than 10% of the climate impact of a system over its lifetime, the transition from HFCs to next-generation refrigerants must also consider equipment performance, specifically energy efficiency and capacity. It is imperative that these new refrigerants help equipment manufacturers meet increasing efficiency levels prescribed by government-mandated minimum energy performance standards. At the same time, there is common agreement that refrigerants must be safe to transport and use, be reliable, and be cost-effective. Two international treaties, sponsored and administered by the United Nations, currently affect the HVAC in our industry. The Montreal Protocol will be complete in 2030 in developed countries and by 2040 in developing countries. Overall, the Montreal Protocol has achieved 90% of its goals, and due to its adoption by every UN member, it is considered an exemplary international treaty. The Kyoto Protocol commits signatories to reduce greenhouse gas emissions. However, because of the Montreal Protocol's proven track record and wider ratification, it has superseded the Kyoto Protocol as the more practical means for phasing down HFCs. In 2016, the Kigali Amendment to the Montreal Protocol was passed, providing a predictable, rational framework for the phase-down of HFC production and consumption by more than 80% over the next 30 years. This agreement has been ratified by 69 countries and the EU and is effective this year. According to the UN, global compliance with the Kigali Amendment could help avoid a half-degree Celsius rise in global temperature before the end of the century. This chart shows the phase-down schedule of both the Kigali Amendment and the European Union fluorinated gas regulations, known as the F-gas law. The F-gas law on the far left is currently enforced, and as I mentioned, the Kigali Amendment was enacted on January 1st of this year. Alternative refrigerants currently identified for the Unitary and VRF products to meet GWP goals for the first two reduction steps will only be intermediate solutions as industry progresses toward a final GWP goal. The most important long-term action is to use lower GWP alternatives in all new equipment and to do this as early as possible. I would also like to emphasize that this transition is a phase down and not a phase out. All refrigerants allowed for use in Unitary and VRF systems today will be available for the life of installed equipment. The European Union implemented the F-gas regulations with the objective to cut availability of HFCs by 79% between 2015 and 2030. This will be achieved by phasing down the amount of bulk HFCs that can be placed on the market in 3 ways: through gradually reducing quotas for F-gas producers and importers, through bans on HFCs and new equipment for certain sectors, and by strengthening of obligations on containment measures such as leak checks, repairs, recovery, and training. One lesson learned from the initial phase-down steps, which were marked by shortages and price increases, is that a lack of early sector controls results in a less orderly transition. In Japan, the law concerning the protection of the ozone layer was revised in 2017 to comply with the Kigali Amendment and is to be enforced this year. The Act on Rational Use and Proper Management of Fluorocarbons specifically covers the phase-down of HFCs and includes the targets shown for designated products. To date, Japan is well under its Kigali Amendment obligations for HFC reduction. Limits for VRF systems will be determined this year. It is expected that the cap will be a GWP of 750 and a target year between 2025 and 2027. Japan has supplemented their phase-down efforts with a significant investment in risk assessment studies on alternative refrigerants and assessments of safety, environmental performance, energy efficiency, and economic feasibility. Moving on to North America, Canada was among the first countries to ratify the Kigali Amendment and aligned its HFC phase-down in step with its guidelines. The regulations also contain product-specific GWP caps that apply to new commercial refrigeration equipment in 2020 and chillers in 2025. At this time, there are no similar plans for Unitary or VRF equipment. The U.S. ratified the Montreal Protocol in 1988, but has not ratified either the Kyoto Protocol or the Kigali Amendment. SNAP is EPA's program under the Clean Air Act to evaluate and regulate substitutes for the ozone-depleting chemicals that are being phased out under the Montreal Protocol. SNAP Rule 20 in 2015 and Rule 21 in 2016 prohibited certain substitutes based on GWP to encourage use of climate-friendly alternative refrigerants. These rules and the Section 608 Refrigerant Management HFC rule provided direction for the 10% and 40% HFC reduction steps in line with the Kigali Amendment. However, Rules 20 and 21 were both partially vacated in the U.S. Court of Appeals based on a decision that EPA does not have the authority to regulate HFCs that were previously listed as replacements for ozone-depleting substances. The EPA has also proposed to revisit the refrigerant management requirements so they would apply to CFCs and HCFCs only, but not to HFCs. EPA is currently in the process of redrafting the SNAP 20 rule and will also redraft the SNAP 21 rule in response to the latest court decision. EPA is also expected to release a proposal soon on how it intends to implement its authority on HFCs under the Clean Air Act. Individual states are not preempted by federal authority in the regulation of chemicals for environmental purposes. The uncertainty of the SNAP program and lack of federal direction with respect to the HFC phase-down has led several states to enact or consider their own regulations. California has taken the lead by adopting the commercial refrigeration prohibitions from the SNAP rules, which were vacated. More importantly for Unitary and VRF equipment, California has proposed a ban on refrigerants in stationary air conditioning equipment with a GWP greater than 750, effective in 2023. Other member states of the U.S. Climate Alliance, such as New York, Connecticut, and Washington, have announced plans to reduce greenhouse gas emissions, including proposals for the phase-down or phase-out of HFCs. As you can see, the U.S. is currently in a state of flux. There are still many questions to be answered with regards to this HFC phase-down. Thank you. Jennifer?
And thank you, Doug. You gave us a lot of ground to cover with respect to global regulation and policy issues, so let's explore further in our first roundtable of the day. Our first question, there's a mix of published GWP values. Which ones are acceptable? Sarah, would you like to start us off today?
Sure. So there's a scientific intergovernmental body called IPCC, and they periodically publish GWP values of molecules and their assessment report, or AR. And the F-gas regulation references the fourth version, which is AR4, and their high GWP refrigerant phase out and bans. But the most recent version is AR5, and it's a more comprehensive list of molecules, and it includes some of the newer low GWP HFO molecules. So oftentimes in the industry talks, you would see people referencing both AR4 and AR5.
Yeah, and and adding some more confusion, Sarah mentioned AR4 and AR5, so obviously there was a 3, 2, and a 1, and so there's still values that people pick up and use there. So you have to be careful and mindful of what value you're actually looking at, and a lot of people don't really put the assessment report number behind it. And we're also approaching another assessment report, and there'll probably be some new values as science improves understanding the atmospheric life of these molecules and how they interact.
Okay, so continuing with that, how are GWP values of blends determined? So you've given us all these values, but how do you get those numbers?
Yeah, so you pick the assessment report for the molecule you want. So for example, in the assessment port 5, R32 is 677, so you take that value times its weight in the blend, say R410A, 50%, you get a number. You take the 125, that's the remaining 50%, times its GWP value, and add those together, and that you end up with that value for that assessment report. So blends are always calculated, they're not actually in the assessment reports.
Okay. Next question, how will the Kigali Amendment affect the refrigerant transition in developing countries? I think, Doug, you're the one to go to first on this one.
Yes, so many developing countries, including China, will start their freeze of HFCs in 2024. And other countries such as India and those in hotter climates will start their freeze in 2028. So because there will be a large increase in HFC production and consumption, it was important to have both India and China in the negotiations leading up to acceptance of the Kigali Amendment. There will be phase down in the developing countries that will be delayed, that will give them time to adapt to technological changes, and it will also allow them to adapt and get set for the costs that will be required for the HFC phase down and adoption of new refrigerants.
Okay. Moving on, Doug mentioned earlier that Japan is ahead of their Montreal Protocol HFC phase down goal. What are the challenges and concerns moving forward?
Yeah, so I think the challenges these are phase down schedules, and so as technology develops around refrigerants, some refrigerants still have some elevated GWP, and so as you look at the phase down schedule, as we get further out, like to 2028, we have to be below certain limits. And even though we adopt refrigerants, say they're going to be considered interim refrigerants. So a good example would be R32 with a GWP of 675. Doesn't quite get you there for the next phase down. So in 2028, new technology around refrigerants or refrigerant blends will have to be introduced to meet that next phase down. Now what's interesting is you're going to end up with a fragmented marketplace with different refrigerants, different technologies, and then going back to Doug, with the developing countries, they get to pick and choose what is actually happening because their phase down schedules are a little further out.
Okay.
So.
All right, let's move on. California is proposing a 2023 phase out of 410A. How will that affect the marketplace? Doug?
Yes, so if California does proceed with their 2023 date for the phase out of refrigerants with a GWP of less than 750 for stationary air conditioning equipment, it will result, as we've mentioned in other markets, a fragmented market in the US, where certain equipment will only be allowed to be sold in California and would not be compliant in other states until those jurisdictions catch up with the code adoption process where they can use refrigerants that we expect to be flammable refrigerants.
Okay, that's something we'll address later as well.
Yes.
Correct? All right. Next question. How is the F-gas quota affecting refrigerant selection and transition? Sarah, you want to start this one for us?
So the F-gas, since the F-gas regulation was enforced, the first major quota reduction was in effect in 2018, and so that led to a lot of market confusion and increase in quota costs. And so for equipment manufacturers who are using higher GWP refrigerants, that kind of became an added cost burden for them. And so they decided to switch and go to lower GWP refrigerants, although it's ahead of the transitional band or higher GWP band schedules.
Yeah, so the mechanics in the marketplace were kind of interesting. So as you approach a phase down, people start to prepare around the quota. There's only so much to go around, and people start having some unusual consumer bad behavior, start hoarding, or don't know what the future is going to lie. So prices really jumped because they moved from a cost base of production to a GWP-based weighted average. So if you had a high GWP refrigerant like 404A, you paid a lot more for it than something that was half its GWP. And so the marketplace started to adjust to that. In this year, as we've now moved a year further, the marketplace has adjusted to that, and prices has restabilized. But it's driven a lot of fragmentation. So people are adopting new refrigerants, and sometimes 2 different refrigerants in the same marketplace, or even 3, and different products and different technology. And so the good news is here, I think the EU has given us an experiment to see what the rest of the world is going to see, and maybe we can put other controls in place that help that transition to be a little bit more smoother for the rest.
All right, well, that brings us to the end of our first roundtable discussion. Thank you to all of you. Now, Sarah Kim will walk us through Unitary HVAC market evolution and global trends. Sarah?
Thank you, Jennifer. So as part of the market evolution, I would first like to touch on North America and Europe R22 transition history, as some of the refrigerant driving factors at the time will also apply to 410A transitions in Unitary and VRF equipment. Multiple factors were considered during the phase-out of R22, such as ODP regulatory phase-out timing, safety and performance of alternative refrigerants, refrigerant and hardware availability, and investment and equipment costs. While many solutions were available, 4 options emerged as most viable. 404A was not ideal for Unitary and VRF because it has much lower thermodynamic efficiency than other proposed products such as 407C, and minimum energy efficiency standard requirements put pressure on its use. 407C was not ideal because of issues with high glide, where different components of a blend evaporate at a slightly different temperature, which can negatively impact system efficiency and can complicate service in case of a leak. And R32 was not chosen because of its flammability. 410A became the preferred solution, being a non-flammable and very low glide blend, even though it had significantly higher discharge pressures compared to R22. That being said, let's look at the AC refrigerant usage today in new builds across the globe. In North America, 99% is using 410A, with less than 1% using next-generation flammable refrigerants, R32 and R452B where allowed, which are units with very small charges such as window units. In South America, the 410A to R22 ratio is 4:1, where R22 is mostly being used in Argentina and Brazil mostly using 410A. In Europe, 410A and next generation products have about a 50-50 split. China has an interesting distribution landscape where 50% of new builds are using HCFC R22, 40% uses HFC 410A, and remaining 10% using R32, a lower GWP HFC product. Japan market shows the highest conversion into the next generation of refrigerants, where R32 accounts for 90% and only 10% using 410A. Southeast Asia is using a mix of 410A, R32, R22, similar to China, but 410A being the dominant refrigerant with 85% usage. In Australia and New Zealand, about a quarter of new builds converted to R32, but majority is still using 410A. In Middle East and Africa, R22 is predominantly used, which is a great refrigerant for high ambient regions, but with ozone depleting potential. Before taking a closer look at the Unitary market by region, I would like to briefly go through different types of Unitary equipment. Mini-split units have one outdoor unit and one indoor unit for single-space cooling needs. On the other hand, multi-splits typically have one outdoor and multiple indoor units. VRF, or variable refrigerant flow equipment, are used for light commercial buildings, which allows individual temperature control of indoor spaces. Rooftop or package units are also used for buildings where cold air is delivered to indoor spaces through ductwork. PTAC stands for Package Terminal AC, which should be familiar to frequent travelers for their hotel room cooling needs. Ducted split units are the most dominant technology used in residential spaces in North America, where cool air is delivered to individual spaces by blowing cold air through ducts. And finally, portable units are also considered unitary equipment. Technology selection for HVAC equipment depends on regional needs and room and building requirements. Regardless of the type of equipment shown here, the refrigerants currently being used are mostly either R22 or 410A, depending on the Montreal Protocol phase-out schedule. However, as mildly flammable lower GWP refrigerants are introduced in the market, it is expected that the market will be fragmented due to the charge limits of these refrigerants based on equipment safety standards, which Doug will discuss in more detail during his second presentation after the break. Let's dive deeper into specific geographic regions. In the U.S., as mentioned earlier, ducted split units are dominantly used in residential spaces, and VRF and rooftop units are the main equipment used in commercial settings, which all use 410A in new builds. Of course, chillers are widely used in commercial building cooling needs, but for the purpose of this webcast, I will be focusing on unitary equipment only. In the U.S., a significant aftermarket of R22 still exists. Transition to lower GWP refrigerant will be slow without regulatory push and change in codes and standards. A closer look at market segments in the U.S. shows that nearly half of the unitary application was accounted for ducted split residential units, shown in blue. Heat pumps, shown in green, take up a significant portion with about 1/3 of the U.S. market, where the refrigerant flow can be reversed and provide both heating and cooling needs throughout the year. Remaining 15% represented VRF, mini-split, and rack, which are room ACs such as portable or window units. Based on 7.8 million unit sales estimated by ASHRAE, residential sales accounted for 96% as shown in blue, and commercial units only accounted for 4% of sales. However, in terms of sales in dollars during the same period, the residential to commercial unit sales was about 2-to-1 ratio. In Asia, market uses a mix of mini and multi-split ductless and portable units for residential, and VRF systems for commercial cooling needs. Transitions from 410A to R32 are well underway and very advanced in Japan, as mentioned earlier. R22 still remains in service, though shrinking, and many nations have adopted 410A or R32. Codes and standards allow usage of A2L and A3 flammable refrigerants in some countries. China accounts for the majority of sales and exports in Asia, with 61 million units sold in 2017 for domestic usage compared to 7.8 million units sold in U.S. during the same year. Mini-split, multi-split pack units represented 81% of sales, shown in orange, and VRF being the rest in blue. Although VRF represented 1/5 of the sales, due to the market size, the VRF sales in China alone exceeded the total unitary equipment sales in the U.S. in 2017. During the same year, 110 million units of unitary equipment were produced and exported from China, which were widely distributed across the globe, with North America in green, Middle East in yellow, and Europe shown in dark gray, making up almost 50% of the exports. Finally, in the European Union, equipment usage and needs are similar to Asia, with mini multi-splits mostly used for residential and VRF for commercial buildings. Major transition is underway due to F-gas regulation and quota costs. R32 is expected to represent more than 50% of refrigerant used in new equipment in 2019. However, R410A will continue to be used in new builds, and also a significant aftermarket will remain. In 2017, the market size was slightly smaller in European Union compared to the US, with 6.4 million units sold, where 92% represented residential AC as shown in blue, and commercial units such as PAC and VRF accounted for 8% of units sold. This concludes my talk on unitary HVAC market evolution and global trends. Back to you, Jennifer.
Sarah, thank you so much. Now, Steve Kujak will take us through a quick evolution of unitary refrigerants and a little forecast into possible replacements in his presentation, Unitary Refrigerant Transition History and Selection Challenges. Steve?
Before we get into the discussion around potential replacements for R410A and R22, let's again review the R22 to R410A history of that transition and the alternatives and the selection challenges that that transition offered when ultimately R410A was the refrigerant of choice. The drivers for this GWP transition mirror the last ozone depletion transition, and that regulation is driving a change to refrigerants with the same factors of safety, performance, alternatives, and candidates, hardware and technologies available being primary drivers for trying to sustainably balance the need for investments and equipment costs. In the end, R410A was found to be the best replacement for R22, but how did we get here from an equipment design standpoint? If you look at the various safety and performance factors that R22 alternatives offer, it becomes clear on why ultimately R410A was selected by the industry as the best solution. Unfortunately, R410A hardware technology was the limiting factor in the early adoption because it was much higher pressure than R22, and thus the available system designs could not be used directly with R410A. The investigation for new low GWP alternatives started with candidates that have similar capacities to R22, and like in this transition, it will be similar. New alternatives will be evaluated for their compatibility for use in R22 capacity and R410A-like capacity ranges. With the next transition to low GWP options, as an industry, we are coming to accept some degree of flammability. So R32 is now being considered again as a replacement option. However, many new blends are emerging as possible solutions. The industry continues to seek ASHRAE Standard 34A1 or B1 non-flammable options, and the potential transition path is unclear, and there are many possible paths. In this webinar, we will discuss the various candidates that are emerging and the trade-offs that they provide. Interestingly, the options we will present the industry with the same trade-offs of safety, capacity, efficiency, and glide, and hardware development the last transition provided. Let's talk next about the challenges in selecting new refrigerants for use. There are many factors to weigh around safety and reliability, sustainability and efficiency, and the availability and affordability while balancing all the need for the ever-changing needs for customers for greater operational performance and comfort. Considerations are needed to balance are the following: environmental considerations, safety consideration, design considerations, and sustainability. Challenge is selecting the refrigerant with the best balance of all these issues. To dig deeper around these higher level requirements, equipment designs are further challenged to look for the refrigerants with the best balance of technology considerations around them. For example, safety, toxicity, flammability in that area. This transition is this is a consideration in this transition, and this is by far will be the most challenging. Design considerations like operating pressure, chemical stability, materials compatibility, compressors, lubricants. Interesting, lubricants were the last transition's most challenging issue, with new lubricants had to be developed, and in this transition, this is a concern as well, but to a much lesser extent. Of course, there's always heat exchangers and heat transfer we have to worry about, thermophysical properties around capacity, efficiency, and glide, and compressor discharge temperatures, and then the exact cycle design, the refrigeration cycle we want to use. So optimizing refrigerants and the design for the best solution is the ideal way to select refrigerants. Next, we'll focus on the new refrigerant technology and alternatives that are developing by first starting with the new refrigerant technology that has emerged. Here's a table of all the available single refrigerants, both old and new, as well as the HFCs, the HFOs, and the non-fluorinated or natural refrigerants by GWP groups, and also by the various concerns and issues that need to be considered when you use these individually. So as you can see, items in blue are the new fluorinated refrigerants that have emerged for this transition. There are 10 new as well as some older discarded refrigerants from the past transition that are part of the discussion in the toolbox, as you see here, for consideration. Many of these new molecules are not ideal for use in unitary products as replacements for 410A. Next, we'll look at all these various alternatives that have emerged as replacements by GWP versus compressor displacement. This is a chart of all the alternatives by GWP compressor displacement by ASHRAE Standard 34 safety classification. I will summarize the best candidates in the next slide and not focus on all these candidates. You don't need to read all of these, and I will summarize in a minute. ASHRAE 34 classifies refrigerants as either A or B toxicity class and non-flammable class 1, and by various flammability classes 2L, 2, and 3. Ideally, an A1 refrigerant is the best choice in this area of interest with similar compressor displacements, i.e. capacities closer to either R22 or 410A. Unfortunately, to meet the GWP phase-down goals of the Montreal Protocol, the refrigerant chemistry does not allow for the low GWP without the trade-off of becoming flammable, with most candidates being ASHRAE 34 Class 2L. Shown on the chart is a region of flammability of alternatives developed when trading off compressor, displacement, and GWP. Next, we will focus in directly to candidates that have emerged for both 410A and R22 that have been evaluated by the industry. This is the same slide as the last, but focused in for compressor displacement similar to R22 or 410A and by the best emerging candidates. Like in the last transition, R22 to HFCs, there are two compressor displacement areas of interest. One is that is R22-like, e.g. like R407C and 404A, and one that is 410A-like, or in this transition, will be in that general displacement area. I will discuss the details around 410A-like alternatives like 466A, R32, R452B, and R454B, while Sarah will discuss potential R22-like alternatives, R444B, ARM20B, and R454A. The major trade-offs will be a GWP versus temperature glide versus the amount of capacity or compressor displacement. With 410A-like having similar compressor displacements to 410A, and the R22-likes having compressor displacements similar to R22. As you can see in the graphic, the R22 candidates have 30% less compressor displacement or capacity than 410A-like refrigerants. Now, one thing I talk about is, so how does the glide impact the HVACR system? We could spend a lot of time in this webinar on this topic. Glide can impact the system in many ways. Glide really comes down to how close a heat exchange approach temperature you can obtain versus the air temperature. Servicing the units is also affected. If you have a leak, then the refrigerant composition can shift, and the impact of understanding how to set the right parameters like subcooling and superheat to understand how well the unit is performing are difficult. Efficiency is really unaffected by the changes in the composition, with capacity being the largest impact. So there are more details to discuss, but in the end, lower glide, the better. But small glide, less than 5 degrees, can be Fahrenheit or 2.5 Celsius, can be an advantage since the impacts are different between the condenser and the evaporator, and I will leave it at that for now. Like the last transition from R22 to 410A, there are two capacity areas of interest with the same glide trade-off. Thank you very much, Jennifer.
And thank you, Steve. Now it's time to hear from you. If you have a question for our panel, please use the interface on your screen to submit it. Please refer to topics we've discussed in part 1 of our webcast. All right, panel, our first question is, to meet California's proposed 2023 GWP requirements, does that mean we must use flammable refrigerants? Doug, why don't we toss this one to you to start?
Yes, so the 2023 date does give us some time to see if there might be alternative refrigerants that are non-flammable, but all of the currently identified alternatives to 410A with an approved ASHRAE 34 and ISO 817 designation are either A2L or A3 refrigerants.
Okay, but what effect does that have on the marketplace?
Yeah, so we have we'll talk about later, we'll talk about 410A replacements, and we have potentially 3 different replacements. And so you could, if we use flammables, we could introduce different refrigerants into California while shipping 410A for the rest of the country. People will not shift out of 410A without regulatory pressure. So the rest of the country will sit in 410A while we're shipping, and many manufacturers ship different products with different refrigerants into the California marketplace, which leads to what we talked about earlier about fragmentation in the marketplace.
Right.
Maybe some differences in how we service equipment, and then some confusion. Meanwhile, as we hit that 2023 date, we have to keep in the mind, in the back of our heads, we have this other 2028 date that's coming in the Montreal Protocol, which phases us down some more.
Okay.
And we'll have to, likely, I mentioned a little earlier, we may have to phase out of those as well. Or the ones we're putting in the marketplace right now, phase out then again 5 years later. So
Okay.
quite a burden.
I see. All right, let's go to our next question. Explain again the difference between phase down and phase out. Who would like to start with this one?
I can answer that one.
Okay, great.
So the previous transition under the Montreal Protocol for the phase out of CFCs and HCFCs set a specific deadline where there would be no more production or consumption past that date. For this HFC phase down, there will be a period of time, hopefully permanently, for the market to have available refrigerant to service existing equipment. So there will be a GWP-based percentage that stays the same indefinitely. So we can still produce HFCs for those pieces of equipment still in installation and service.
That just means the volume's way down.
And so what's really interesting in this transition, though, is in the ODP, they identified specific chemicals that would be eliminated that had ozone depletion. We still use some chemicals today that have de minimis or next to zero ozone depletion that aren't on that list. And so with the HFC phase down, you may have a high GWP material that you still use to give you a good attribute as long as you can keep the GWP down. So you end up with a little different, from my standpoint, from a technologist, a bigger playbook,
Okay.
To be able to create the optimized blends that we like to create.
Okay. Well, Steve, this one is directed to you. You said that in 2028, the GW for R32 will not get you to the GWP requirement of Kigali. What GWP limit will be needed?
Okay, so that's a great question because we have that debate already about, as you have this basket of gases and when you add up all the GWPs by how you use them, your GWP value by country is around 2,000. And so if we want to get to 85% phase down or 15% left, we have to get to somewhere around a 300 to 400 GWP average of basket of gases. But we also have to remember, too, that we keep using more of these gases as countries grow, so we have to be maybe less than that. I think a lot of people have talked about a GWP target that would be acceptable for 410A or R22 replacements around 300. It would be a long-term acceptable limit. I mean, the industry is trying to find limits, but that's a good target to shoot for and try to get under that limit. And Sarah will talk about some stuff that's around 300.
Right,
later.
so I think we kind of included that in part of this webcast because we thought it's important to talk about this because people are going to say, well, the current options that Steve is going to talk about probably would not meet the long-term Kigali step-down goal. And so, although it's still in the developmental phase, we thought it's important to mention it. So we'll be discussing it during the second part of the presentation.
Very good. All right, next question. Will the Montreal Protocol be amended to reference IPCC AR5 or future AR6 instead of AR4?
Well, I think that's difficult because in the EU F-gas law, it's actually written in the law, so you have to amend the law.
Okay.
Now, some countries can pick and choose what they want to use, but I think everybody's aligning around AR4. But I think at some point we're going to have to, as science develops, people are going to have to call out exceptions to different GWPs because some of them can be significantly different from each other.
And then I guess for the next generation HFO products, there is some single-digit values for the AR4 value or AR4 report, but in the AR5 they're 1 or less than 1, so it's even lower, right? So there might have to be some revisit in the law.
Okay. Onward, how is the GWP calculated in the assessment reports for non-blended refrigerants?
Yeah, so you want to go ahead, Sarah? Or? Okay. I think it's a scientific-based amount, right? Okay. So you have it really in two components. So a molecule absorbs heat in the atmosphere through the infrared absorption from the sun and keeps it in the atmosphere and reflects it back. So a molecule is measured that way, but it's also how long it stays in the atmosphere so it can continue to do that and regenerate the heat back in the atmosphere. So the target here is to have molecules with, well, you can have a high infrared absorption, but have a short atmospheric life, and it doesn't contribute too much. Or, like we have today, when we developed HFCs, they have long atmospheric lives, and their absorption spectrum is pretty good too, but it's still less than the original refrigerants like the CFCs we phased out. They had very high GWPs. And so we already did a phase down in GWP indirectly, because the old refrigerants like R11 and R12 had GWP values of 10,000, 14,000, and we're talking about 4,000, 2,000. Now we need to get down to 300. So you can see we've already stepped down inadvertently, but these gases still are too long of atmospheric life and too much infrared absorption.
Okay. Next question, with the R22 R410A replacement cycle, should I keep my R22 equipment until the final replacement is available? Doug, you want to jump in on this one?
Yeah, that's an individual choice. Okay. I think that it's up to the consumer to decide whether they want to go with the newer technology right now or if they want to stick with what they've got until the phase out is necessary.
Yeah, and I think you really, if you're a large user of a different equipment on your building or in a complex, you should have really a plan, right? So you're going to have some R22 equipment. You should already have a plan in place to replace that to 410A or as its useful life. And don't wait, because the new equipment's going to be 30% more efficient, 40% more efficient. So you got to take advantage of that efficiency from the indirect energy standpoint as well. Now we're moving into another phase. Now we're going to have to start thinking about in a few years, how can we incorporate both plans, right? I have some R22 equipments on critical use equipment. Maybe I'll keep it going longer. I got 410A being replacement in smaller units or anything like that. Oh, by the way, I'm going to have new equipment. Let's say it's R32. Oh yeah, we'll start phasing that in, and we might have a more comprehensive plan potentially. But I think you shouldn't wait, because sometimes you might have to wait till 2028, which is 9 years from now, to get the final solution. And a lot of your equipment, you're leaving a lot. Your energy bills are going to be higher. You're being less sustainable. You're running reliability issues because the equipment might now be 30 years old because you waited 10 years because it's 20 now. So
personal decision.
Personal
basically,
decision.
Yeah, depending on your situation. What portion of research and development is done with actual refrigerants versus computer modeling?
Yeah, I can start that start the answer. So we in the developmental phase, we kind of use the modeling tool as our guidance because we have to start somewhere. We usually come up with multiple potential plans, and we look at it in a modeling perspective, and then we narrow it down to a couple promising refrigerants. We still like to test it in real equipment and see how it performs because in the modeling, not all of the factors are considered. But so I would say, modeling is the first screening tool, and then we would move on to the experimental phase, and then we also share it a lot with equipment manufacturers as well.
Yeah, so it's interesting. When I started back in 1992, a lot of times we had properties, but we didn't have the modeling capability or very limited model capability. And so it's a lot of trial and error. Okay. It's like, well, I see this happen. What can it be? Now, Sarah will deliver the properties. We have models for our equipment. We model that refrigerant in that equipment, and then we go to a test to validate it. Most of the time we go, oh yeah, it matches the properties, or I don't seem to get the right energy balance on the equipment. There must be something off in the thermal conductivity or the pressure and enthalpy dome. Okay, so we need to go back to Sarah and go, okay, we got to remeasure some properties, stuff like that, and adjust it. Or a lot of times we just adjust it ourselves and give a little offset.
Yeah, that's very good feedback because potentially it gives us space to improve our refrigerant, and so we can make it better in terms of properties, or we'll talk about glide later, but we can improve on glide or efficiency a little bit. So it's it's a lot of back and forth. And
But it's quicker back and forth.
yes, definitely.
Versus the old days. It's a lot quicker. It can be hours and days feedback
Okay.
versus weeks and months.
That's a huge difference.
Yep.
All right, next question. With the cost to replace existing refrigerant equipment, do you anticipate any associated tax breaks or incentives to help accelerate this transition? What do you think, Doug?
That's a good question. Right now, in the United States, we don't have any current residential tax credits available for energy-saving products in the HVAC in our market. There are some commercial tax incentives available, and most of the utilities will have rebate programs for new equipment. So I don't expect under this current administration to see tax incentives of this nature, even though we are transitioning. By the time we do transition for most of the country, there may be incentives available. I think that would be a nice thing to have to make this progression forward to new equipment.
Okay.
So Doug, do you think there'll be incentives ever, I think, based on the refrigerant that you choose? Not sure.
Not specifically the
Yeah.
refrigerant, but
the equipment
with
for energy
updates
efficiency.
for new energy efficiency
Yeah,
equipment
so I don't
would
think,
be,
I mean, it'd be nice to have a refrigerant-based target for replacement, because it would drive more incentive to move faster, right?
Yeah, one thing we didn't mention is that in addition to the HFC phase-out, we've got new residential energy efficiency metrics coming into effect in 2023. So things are progressing towards a stage where everything's going to hit at nearly the same time.
It's hard to do both.
So it would be hard to do both, but we're going to have to adjust, and it would be nice for consumers to have these incentives.
Have we ever had incentives like that, or we haven't seen that in your career?
Not refrigerant-based,
Okay.
but for certain equipment of efficiencies, higher efficiency equipment, there are certain rebates and tax incentives available.
All right, next question. What is the difference between 400 and 500 series refrigerant blends? Sarah?
Yes, so
Yeah.
I can take that question. Essentially, they're both refrigerant blends with at least two components in it. And so the 400 series, they respond to zeotropic blends, and 500 series, it's azeotropic blends. And if you look at the number of refrigerants that are under the 400, 500 series, they're very dramatically different. So in the 400 series, at the moment, I think we go up to 467,
Yep.
right? And in the 500 series, we're at 516. And so the reason for that is because the zeotropic blends, we're going to talk about Glide a little bit later, but the components of the refrigerant boil at a slightly different temperature, and so it creates this glide that we call, that difference in boiling temperature in the evaporator and the condenser. Whereas the azeotropic blend for 500 series, the components kind of interact with each other, and so they boil at the same temperature like a single molecule. And so for those blends, we give it a 500 value.
Okay.
Yeah, and I think, I can expand a little further. I think people always ask me, why 410A? Why 410? And so the nomenclature doesn't tell you anything about what's in the blend. It's just you were the 10th person in line. It was unique. So we gave you the 10 number. And then you were the first A of that blend. So 410A is 32 and 125. There's a 410B with a different composition. And then when you move to some of these series, so we're up to 67, but we're really over 100 refrigerants in the 400 series, because in the 407 series, which a lot of people are probably familiar with, we go from A to I. So we have whatever that is, 11 different refrigerants with the same composition of R32, 125, and 134A.
All right, well, this concludes our first question and answer segment. We will have one more Q&A segment later in the webcast. We will now take a short break before we begin part 2 of this ASHRAE Webcast, the future of refrigerants in unitary and VRF systems. Part 2 of our webcast will begin in 5 minutes. We'll see you then. Welcome back to today's ASHRAE Webcast, the future of refrigerants in unitary and VRF systems. Once again, our panelists are Doug Tucker, Director of Industry and Government Relations at Mitsubishi Electric US, Sarah Kim, Scientist at Arkema, And Steve Kujak, Director of Next Generation Refrigerant Research at Ingersoll Rand Train. In part 2 of today's webcast, Steve and Sarah will present on low GWP refrigerants, after which our panel will have a roundtable discussion. Doug will present on flammable refrigerants, and we'll hear from you, our viewing audience, during our final question and answer segment. So, where has the HVAC industry been with respect to refrigerants, and where do we think it's going? Low GWP refrigerants seem to be the direction, and here is Steve Kujak to discuss lower GWP R410 alternatives. Steve?
Thanks, Jennifer. My discussion will focus on lower GWP 410A-like alternatives. One of the things I will point out is all the 410A-like alternatives that you will quickly realize is all of the alternatives contain large percentages of R32 refrigerant, including pure R32 as well as being a candidate. Remember, 410A is roughly 50-50 blend of R32 and 125. The 125 is added to the 32 as a non-flammable agent, which renders the blend to be non-flammable at all conditions of use. In many cases, as I will present, R32 is blended with other refrigerants to optimize various features of the blended refrigerant. These include flammability, GWP, capacity, and compressor discharge temperature, and to a lesser extent, glide. All the alternatives I will review have been thoroughly investigated by the industry from an equipment performance standpoint. This slide was shown earlier and visually shows the alternatives reviewed by the industry when moving from R22 to HFC candidates. In the end, 410A was adopted because it had the lowest temperature glide of all the non-flammable blended candidates. R32 is flammable, but was discarded in the last transition. As we discussed earlier, R410A has 30% higher capacity than R22 and was not initially adopted as a candidate because of the need to develop new components that were compatible with the higher pressures and displacements. 404A and 407C were discarded in most cases because 404A was too low in efficiency and 407C had too much temperature glide. Shown is a summary of the 410A candidates comparing efficiency, capacity, compressor discharge temperature compared to 410A. R410A is used as the baseline and is 1.0 in the chart. These are theoretically calculated values in the table. When drop-in tests are performed on these refrigerants, you get different results and the impacts because of heat exchangers and compressors designs that are used in those. It can be very confusing for people making claims on better efficiency and capacity. In the end, all these refrigerants will have slightly better efficiency than 410A because their thermodynamic efficiencies are higher. If a certain refrigerant is selected for use, the capacity of the system in the design is adjusted to the same as needed. Smaller compressor or slightly larger compressor. And in the case of operating MAP needs, the compressor discharge temperature may or may not need to be mitigated for some of these alternatives. So we have 4 lower GWP alternatives at this point that are 410A-like. Like I said earlier, these are mostly blends of R32 with other refrigerants to optimize performance or other attributes like flammability, GWP, or compressor discharge temperature. R32 is the exception since it is a pure fluid. Working from left to right, let's review the candidates. The first candidate on the left is R466A, which is a blend of R32, 125, and R13I1, with a composition of 49% R32 with non-flammable agents of 125 and R13I1, or what people have been reading in the literature as CF3I, to make it a non-flammable refrigerant blend. This will be the only refrigerant in this class that will be non-flammable and have a GWP of less than 750. Capacities and efficiencies are similar to 410A, and the glide is less than 3 degrees F. 452B blend is a composition of 32, 125, and 1234 YF, which is a 2L flammable refrigerant with a composition of 67% 32, with the addition of 125 and 1234 YF to optimize properties. Capacity and efficiency are similar. Glide is less than 3 degrees like the previous. R452B was developed because it was optimized to work with the current 410A lubricants, and it can be considered as a true drop-in replacement for 410A designs. The next candidate is 454B blend, and it's composed of R32 with 1234 YF, with a composition around 69% 32 and the remainder YF. R454B is basically R452B without 125 to lower the GWP to the lowest possible value. Capacities and efficiencies are similar. Glide is once again less than 3 degrees. The 460 GWP value is the lowest of all the candidates, which is the primary attribute of interest with this candidate. 454B does require an optimization of lubricant-free use. And the last candidate, and by far the most adopted candidate at this point, is R32. And it's used in its pure form and it is a 2L refrigerant. Capacity is higher than 410A by about 8%, and the efficiencies are similar. R32 has no glide, which is a plus, but the glides for the other alternatives are not much of a concern since they are small, or less than 3 degrees. All are good candidates to consider, with products being in the marketplace or announced for all candidates except 466A. R32 has been adopted the most, with a lesser extent 454B and then the 452B. 466A has been heavily studied by many OEMs, and its performance is considered similar to 410A. Investigations continue into 466A since the new refrigerant, CF3I, is still under commercial development. Next, let's review some actual equipment performance information on these alternatives. Myself and Dr. Ken Schultz have offered many papers on these alternatives, and this slide summarizes some of the testing we conducted on a 410A air-cooled, water chiller. 454B was also tested in the similar unit configuration before this work, and the performance is identical to 452B and 466A. But all this data shown is from the same unit configuration and allows the direct comparison without control or unit differences. The 410A chiller was soft optimized, drop-in test, with only the refrigerant charge and the expansion device adjusted to allow the better comparisons. The chart on the left is capacity and efficiency, or COP, comparisons with varying ambient conditions at a fixed chilled water temperature exiting condition. Total capacity is on the left axis and the total COP is on the right axis. As you can see, COP for all these alternatives were similar regardless of the change in ambient condition, and all were similar to 410A. Capacities were similar for alternatives to 410A except for R32, which had a higher capacity, but this is as predicted by the thermodynamic properties for 32. The big difference observed was the difference in compressor discharge temperature, which is shown as CDT on the chart on the right. On the left vertical axis is the actual compressor discharge temperature measured, and on the right axis is the change in compressor discharge temperature with ambient temperature as compared to 410A. Based on thermodynamic properties alone, all the alternatives will have higher compressor discharge temperatures than 410A, with pure R32 being the highest. Much has been discussed about the higher compressor discharge temperatures of R32 and whether you need to incorporate into an R32 design compressor discharge temperature cooling. As you can see in this testing, the compressor discharge protection limit of 130 to 135 C was reached with R32 at about 45 C ambient, but the other alternatives did not reach this 410A compressor design limit. Interesting more is if you look at the change in compressor discharge temperature versus ambient temperature and the difference, you see that the R32's temperatures continue to grow while all the other alternatives are unaffected by the changing ambient temperature. This is a result and a function of the differences in thermodynamic properties of pure R32 and blends of R32 with the other refrigerants. 125, 1234IF, and 13I1 are all added partly to reduce the compressor discharge temperatures of R32. The takeaway is these are good R410A alternatives to consider. Only trade-off is GWP to compressor discharge temperature. Efficiencies are similar. Capacities are adjustable to compressor displacement. So where does this leave us in the potential future transitional paths to consider? Looks like we have alternatives available that would allow a transition for 410A to a range of 410A-like refrigerants with GWPs from 460 to about 730. Unfortunately, the Montreal Protocol HFC phase-down needs will require future, lower GWP alternatives to obtain the right sustainable solution. Many places in the world with later R22 phase-out dates are currently transitioning to 410A, which makes those designs compliant with the new R410A-like alternatives. This will allow a smooth transition to these 410A-like alternatives. Handling the flammability aspects of some of these alternatives would have to be considered, but overall, components are compatible with the operating pressures, heat exchangers, and compressor designs. In the end, 2 transitions are likely, with the Unitary product category having an interim GWP and a final GWP step, with plenty of mark and fragmentation, as we discussed earlier, by refrigerant type across the unit product families and by regional global HFC phase-down regulations, with flammability safety needs by application likely driving a lot of difference as well. This wraps up my discussion of lower GWP alternatives for 410A. Back to you, Jennifer.
Now let's go to Sarah Kim to hear about very low GWP refrigerants, options below 300 GWP. Sarah?
Thank you, Jennifer. So as Steve mentioned during his previous talk, refrigerants that meet the long-term GWP step-down goals are R22-like refrigerants. In the HVAC industry, investigations continue in refrigerant development beyond the intermediate 450 to 750 GWP transition step. Again, similar driving factors apply to refrigerant selection. The current proposed options are similar to 407C, which was one of the candidates during the R22 transition period with a higher glide. However, this time the refrigerants are also flammable. Once again, if we look at the GWP versus refrigeration per compressor displacement, which corresponds to the capacity of the refrigerant, the lowest GWP proposed in the 410A-like capacity is 465 and nothing below that. Lower GWP replacement products are needed as there will still be considerable service and aftermarket refrigerants that will consume the quota as well. Refrigerants that have been proposed are R22-like refrigerants with GWP below 300, which will be the focus of this presentation. Propane, or R290, will also be discussed as it is being considered for small charge AC equipment as well. Propane's capacity is not shown on this graph, but should be about 0.55 tons per cubic feet per minute. There are 3 proposed A2L refrigerants below 300 GWP, which are R454A, 444B, and ARM20B with slightly different GWP values as shown in the table. The thermodynamic cycle performance of these plants were evaluated and compared to R22 as well as R290. With R22 being the baseline refrigerant, 454A showed a slight decrease in COP, followed by ARM20B and 444B, but all 3 were shown to be a close match considering the fact that cycle calculations do not include heat transfer or pressure drop effects. R290 showed comparable efficiency to R22. In terms of capacity, ARM20B showed 5% higher capacity, followed by 454A. 444B showed slightly lower capacity, and R290 had a 10% drop in capacity. As mentioned earlier, the proposed plans have higher glides similar to 407C, with ARM20B having the smallest glide at 4.8 Kelvin and 444B having the highest at 7.4 Kelvin. The 3 refrigerants have also been extensively tested as part of the Oak Ridge National Lab High Ambient Temperature Environmental Program. 444B and ARM20B were tested in both mini-split and rooftop units, while R290 was also tested in a mini-split and 454A was only tested in a rooftop unit. The results shown here are all drop-in test results performed in an R22 unit at the HRIA condition. The COP and capacity of the alternative refrigerants are shown relative to R22. R290 showed higher COP compared to R22 when tested in a mini-split, whereas the A2L refrigerants showed slightly lower COP. In terms of capacity, ARM20B provided the closest match to R22 among the A2L refrigerants, while R290 showed about an 8% drop in capacity consistent with the cycle calculation. As the test units were designed specifically for R22, performance can be improved for A2L refrigerants in new equipment. Other important parameters for equipment design and reliability are compressor discharge temperatures, shown on the left, and mass flow rates, shown on the right. All values are shown relative to R22. 444B showed higher discharge temperature by about 4 degrees in both rooftop unit and mini-split unit, while other refrigerants showed lower discharge temperatures, with R290 showing much lower values than R22. In terms of mass flow, A2L refrigerants were within 15% of R22 mass flow, suggesting similar or same size TXV can be used, while R290 shows significantly lower mass flow, which will require different parts in addition to consideration of higher flammability of this refrigerant. Among the refrigerants tested, ARM20B was the closest match in discharge temperature and mass flow to the baseline R22 refrigerant. Part of the study also included optimization of the refrigerant charge. For all three A2L refrigerants, about 15% less refrigerant was charged while providing similar or higher capacity than R22, which is mainly due to the lower refrigerant liquid densities of these refrigerants. In conclusion, proposed refrigerants with below 300 GWP are R22-like capacity. COP of A2L refrigerants were slightly lower than R22, which can be improved by designing equipment for higher glide blends. ARM20B showed the closest capacity match to R22 among the A2L refrigerants. R290 showed lower capacity than A2L refrigerants, but superior COP. A2L refrigerants showed matching or improved capacity compared to R22 with lower refrigerant charge. That concludes my talk. Thank you. Jennifer?
Sarah, thank you so much. And it is time for our second roundtable discussion. Our first question is this. You have mentioned Glide, Sarah, and I believe Steve have both mentioned Glide today. Talk to us about what that is and why does it matter?
Yeah, so Glide has been around since the HFC transition, where we had to deal with higher glide blends of refrigerants, and I talked about Glide. And if you have small amounts of Glide, it's manageable, and actually it's advantageous. If it's high amount of Glide, it can have impacts, and you have to adjust for it, or you may have to throw more size equipment at it. So Glide simply is, as the refrigerant enters, a blended refrigerant that's zeotropic, they have different vapor and liquid compositions, and the saturated refrigerant temperatures for each of those are different, and so the temperature difference between the liquid and the gas is called the Glide, and it's usually just a measure of the difference between those. Now, obviously the composition is changing through the heat exchangers, but as Sarah mentioned, some of these have significant amount of Glide, so you may have significant amount of composition shift, and which can impact service and other aspects of how you want to handle the refrigerant.
Yeah, I can add to the service aspect. So, servicing high glide refrigerants can be definitely more complicated. So, in a leak scenario, if your equipment is leaking, ideally the contractor should identify the leak, fix it, recover the remaining refrigerant, and then charge it with fresh refrigerant. But what oftentimes happens is they fix the leak, but they just top it off. And so if you have equipment running on a single molecule refrigerant like R22 or a low glide refrigerant like 410A, it's less problematic. But if you have a high glide refrigerant in your equipment, if you have a leak, your higher pressure components tends to leave faster. And so what's remaining in your equipment is no longer the original refrigerant. And so if you just top it off, the refrigerant inside your equipment is no longer the refrigerant that the equipment was designed for and optimized around. And so that would affect your system efficiency in a negative way, and also potentially affect the lifetime of your equipment.
Important to know. All right, our next question. Next gen refrigerants, can they be retrofitted to work?
Yeah, I think Doug has some experience on this.
Well, I think first what I can mention is that product safety listings for equipment are dependent on one particular refrigerant or set of refrigerants. So regardless of safety classification, even if you're going from an A1 to an A1, you will avoid that product safety listing. unless it's part of the set of refrigerants for which it's listed. Second, manufacturers would not allow retrofit of a new refrigerant into existing equipment if it's under warranty.
Okay.
So that would void the warranty.
Yeah, and I think the bigger issue is I think people are going to be considering flammable refrigerants, and I got a short answer for that. It's no,
Right.
don't do it,
Okay.
because the equipment is designed around a non-flammable, and it's non-flammable refrigerant's really robust to ignitions and sources and all that stuff, where the new equipment that's going to use flammable refrigerants is going to have safety protocols around the design and certification. So we had a big incident here in the 2012 area with people putting propane in R22 equipment. We had a few incidences, and so putting flammables into non-flammables, it's just say no.
Just say no.
I can touch
Yeah.
on that topic. So Steve mentioned for a couple of refrigerants that are 410A like replacements, and most of them are A2L refrigerants that are mildly flammable, so they should not be retrofitted into existing equipment. There was one exception that is proposed to be non-flammable, 466A, which is still pending classification at the moment, but it has a different kind of molecule which contains iodine in it, so we expect that it would exhibit different type of system chemistry. So again, the refrigerants that Steve mentioned should not be retrofitted into existing equipment.
All right, let's see our next question. How would current ongoing transition compare to past transitions, and what are the challenges? We'd like to
I can
start
answer
with
that. So
Great.
unlike the previous transition, we had a clear choice for most applications, which was R410A. This transition, we will not likely see one single refrigerant emerge for all applications as a replacement for 410A.
Yeah, and so you're going to have different refrigerants, but we also mentioned earlier you're going to have different GWP targets that we're going to have to hit for the phase down.
Okay.
And so you're going to end up with multiple refrigerants in the marketplace with different fragmentation. Now the other thing, as the flammability requirements develop, we'll be able to allow different refrigerants in small charge equipments, like hydrocarbons or propane or isobutane, which is used in refrigerators today. If you go to a store, Home Depot, you buy a small college refrigerator, using isobutane typically. So we're already using hydrocarbons in small charge to make it safe. Medium-sized equipment, that's still being debated how much we can do for size and capacity. We can use 2Ls. And maybe in the larger charge equipment, we'll have to do different technology or keep with non-flammables, or more specifically, I get involved a lot in public safety, for transportation of people. So we may have to stay with non-flammables there where, because you just don't know what happens in an accident, or in the safety of the public is paramount.
Okay, very good. CO2 appears to be more and more popular in refrigeration applications. So would CO2 be dominant as future refrigerant in the whole HVAC industry? And what's the major shortcoming of CO2 as a refrigerant?
Yeah, so I'll start with that,
Okay.
and we can bounce this around a little bit. CO2 as a refrigerant's been used for 100 years. It was very popular back in the 1920s and 30s, maybe a little bit before that. When you didn't have to have minimum efficiency standards, whatever worked generation, you used that refrigerant. And then as we move forward, CO2 went out of favor when we developed CFCs, HVACs. Now CO2 is under consideration again. Now the interesting thing about CO2, non-flammable, low GWP fluid, its biggest problem is it just has a very poor efficiency because its critical temperature is very low, and so you operate in this transcritical region for some of the audience that understands this, and you don't turn to a liquid, you stay a gas. And so the efficiency of the unit is very inefficient without throwing a lot of hardware at it. Now the other thing that's happening too, though, CO2 is being adopted in areas and is also being displaced by more efficient refrigerants. For example, bottle coolers and small portable devices, CO2 was introduced in that area. People said, oh, I can get hydrocarbons to work because its charges are small. It quickly displaced CO2 because it was more efficient, and there's minimum efficiency standards in that equipment. So if you look at the AC side of the business, our minimum efficiencies are very high. I mean, I've done a lot of experimental work. You just can't get there from here anymore. So we have to keep choosing things that give us the efficiency runway that we need as an industry.
Okay.
Yeah, and add to that, like Steve mentioned, there's no minimum efficiency requirement in large, like supermarket cooling systems or supermarket refrigeration systems. But if you look at the smaller, cooling equipment, like more beverage coolers or those equipment, they have minimum efficiency requirements, and in those commercial refrigeration equipment, CO2 is not being used because of the poor efficiency as well. So that's why it's not being considered specifically in the HVAC applications.
All right, we're going to try to squeeze in one more question. How does the current GWP transition compare to the past ozone depletion potential transition? And I believe for this one we go to you, Doug, don't we?
Yes, so we will see a stepped phase down rather than a phase out.
Okay.
And primarily, as we mentioned, what we're looking at are the use of flammable refrigerants to replace the current refrigerants in Unitary and VRF systems. So I will be speaking about that in more detail in my next presentation.
Very good. Thank you so much, panel. And with that, we now go to Doug Tucker as he will expand on our discussion of flammable refrigerants. Doug.
Thank you, Jennifer. This transition presents us with new challenges. As Steve mentioned, there is a trade-off between GWP and flammability for the higher pressure applications. And most of the viable lower GWP refrigerants are flammable. In this segment of the webcast, I will provide a brief overview of the current practices in working with flammable refrigerants, with a focus on what's new or different from how we handle non-flammable Class A1 refrigerants. The refrigerants currently used as lower GWP replacements for R410A in Unitary and VRF equipment have an ASHRAE Standard 34 and ISO Standard 817 safety classification of either A2L, lower flammability, or A3, higher flammability. As this transition proceeds, the safe use of these refrigerants requires attention to various risks during the product life cycle. Understanding and addressing these risks are crucial to support the introduction of lower GWP refrigerants as required by the HFC phase-down efforts. The major global manufacturers of ductless and VRF equipment have been using A2L refrigerants for more than 5 years, so rigorous measures have been implemented to assure the safe in-factory charging of products, so the associated risk profile is low. Developed countries have a long history of safe transport of flammable gases in cylinders. The risk profile is relatively low, but somewhat different for bulk refrigerant versus pre-charged systems. A2L refrigerants and pre-charged systems will require measures to prevent ignition of leaked refrigerant during transport. It is important that country regulations utilize the latest globally harmonized system, GHS, guidance to distinguish between refrigerants that are mildly flammable and those that are extremely flammable. The presence of refrigerant and possible ignition sources, together with human interaction during installation and service, present a higher risk. Risk can be mitigated by proper technician training and certification and enforcement of regulations. Product safety standards and installation codes prescribe safe construction and leak containment, mitigating risk during operation. Proper leak detection, clearances from combustibles, separation from ignition sources, and ventilation are some of the methods utilized. However, the risk profile can vary by equipment type and application. For Unitary and VRF systems, the probability of leaks is relatively low, but for VRF equipment in particular, close attention must be paid so the refrigerant quantity limit is not exceeded in the event of a leak into occupied spaces. The risks associated with recovery and recycling of refrigerant and also the decommissioning of equipment is relatively high for the same reasons I cited for installation and service. Finally, as the use of flammable refrigerants increases, risk assessment studies, the development of standardized procedures, and training of personnel on flammability issues are all of utmost importance. ASHRAE Research Project 1807 covers all of these topics in greater detail. The final report was published recently and is available for free to ASHRAE members. Globally, the acceptance of flammable refrigerants vary widely. In the U.S., flammable refrigerants are prohibited in air conditioning and heat pump applications, except for small self-contained room air conditioners and PTACs. Around the world, though, flammable refrigerants have been more generally adopted. R32 is currently in wide use for air source mini-splits and small multi-splits in Europe and Asia. However, certain countries within the EU ban flammable refrigerants of all types in public spaces. In India, there are roughly 600,000 A3 mini-splits where hydrocarbons have been in use for several years. Equipment using A2L and A3 refrigerants are also in wide use in China. Australia, not shown here, allows A2L and A3 refrigerants in small packaged equipment and A2L refrigerants in ductless mini-splits. It has recently transitioned very successfully to the use of lower GWP refrigerants. Worldwide, a significant amount of testing and research on the use of flammable refrigerants has been conducted to assure safe operation. This research has been translated to the product safety standards and installation codes. Product standards, sometimes called vertical standards, cover specific types of equipment within a sector or subsector of the HVAC in our market, for example, residential air conditioners. These standards cover general electrical and mechanical safety, including refrigerant charge limits and safe installation and use. The product safety standard applicable to Unitary and VRF equipment is IEC 60335-2-40, which provides requirements for heat pumps, air conditioners, and dehumidifiers. This standard forms the basis of both regional and country-specific standards, which often will include deviations from the international standard. The 6th edition of this standard was published in January 2018 and added requirements for Class 2L refrigerants. This edition has been adopted in Europe with alterations related to EU regulations. In North America, CANINA is an organization created to harmonize the national adoption of international standards for the US, Canada, and Mexico. This cycle for the US and Canada, the harmonized standards will include requirements for the use of 2L refrigerants, and we expect publication by the end of this year. In addition to the adoption of IEC 60335-2-40, Japan has published comprehensive safety guidelines to define appropriate measures to reduce the risk of ignition and has product-specific standards such as JRA 4070 for commercial systems using A2L refrigerants. Group standards, also referred to as generic or horizontal standards, influence national codes or legislation for safe application and installation practices. ISO 5149, covering safety of refrigerating systems and heat pumps, and ISO 817 for the designation and safety classification of refrigerants were updated in 2014 to cover A2L refrigerants. EN 378 was revised in 2016 to cover application of A2L refrigerants in Europe. The ASHRAE standards for safety of refrigeration systems are slated for inclusion in the U.S. model codes. Standard 15, Addenda D and H were published in 2018 and address 2L refrigerants in both comfort conditioning and machinery room applications. Proposed ASHRAE Standard 15.2p for residential applications of flammable refrigerants has an expected publication date of 2020. Standard 34 Addendum G, published last year, established 2L as its own classification. Standard 34 is adding new refrigerants and refrigerant blends at a very rapid pace. The 2021 International Mechanical Code will not likely include requirements for 2L refrigerants in direct systems such as Unitary and VRF. The earliest we think this can happen will be with the 2024 edition. The 2021 Uniform Mechanical Code may include requirements for 2L refrigerants. This is currently pending approval. If approved, it will facilitate the 2023 transition date planned by California. Once the model codes in the U.S. have been published with criteria for the safe use of A2L refrigerants, state and local jurisdictions will be encouraged to adopt them to expedite the transition to lower GWP refrigerants. In Japan, the High Pressure Gas Safety Act classified A2L refrigerant R32 as equivalent to non-flammable for use in split systems up to 3 tons capacity. Risk assessment for the use of R410A, an A1 non-flammable refrigerant in Unitary and VRF systems is fairly straightforward. The refrigerant concentration limit, RCL, is based on the oxygen deprivation limit, and the maximum concentration possible during the leak of a direct system into occupied space must not exceed the RCL. For systems using A2L class refrigerants, the concentration limits are based on flammability. Refrigerant charge size is the most dependable and controllable mitigation factor, since minimum room volumes are not easily enforced and ignition sources in occupied spaces are hard to control. For example, according to IEC 60335-2-40, a charge size of up to 4 pounds of R32 can be used without installation restrictions. Larger charge sizes require the use of refrigerant detection and air circulation as a mitigation method for dispersing a potential refrigerant leak. Additional measures include shutoff valves in the system to prevent further progression of a leak. Most importantly, harmonization between the product standard and the applicable group standard or installation code is required so that conflicts do not exist which would cause confusion for manufacturers, contractors, and code officials, and possibly delay the introduction of alternative refrigerants. Thank you.
Doug, thank you. And it is now, once again, time to hear from you. If you have a question for our expert panel, please use the interface on your screen to submit it. And our first question this go-round is, there is a lot of discussion on refrigerant blends. Why does the industry need to pursue blends and not a single chemical composition for refrigerants? Sarah, you want to take this one?
Yeah, so oftentimes if you look at single component molecules, it doesn't add to a lot of variety. And so oftentimes when we're looking at next generation refrigerants, we look at how are we going to replace the existing refrigerants. And so we try to match so that when you're designing new equipment for new refrigerants, you don't have to redesign your whole equipment around it. So oftentimes, if you specifically look at single component refrigerants, your choices are very limited. And so if you can blend different components, you can probably match the existing refrigerant. And other important reason for it is in the past, especially when the industry was developing non-flammable refrigerants, in order to make the blend non-flammable, you had to mix a non-flammable component with a flammable component. So that's another reason.
That makes perfect sense. Okay, next question. Has NFPA weighed in on fire suppression requirements of HVAC units using flammable refrigerants? Doug, you've talked a lot about the flammable refrigerants today. So how would you answer this question?
Yes, I would say that NFPA, in addition to the ICC International Fire Code and other organizations that write codes for the flammable refrigerants equipment use, have specific requirements for installation that would be determined primarily by the product safety standard, but all of the associations that are developing the standards, ASHRAE, CSA, UL, they're primarily open organizations. If NFPA or ICC wants to be involved, they can be involved in the development of the product safety standards and the group or installation code standards. So yes, I think there's the opportunity to weigh in. I do see most of the requirements, though, for the flammable refrigerant equipment to be in the product safety standard itself.
Okay. Next question. How will alternate refrigerants affect the pound cubic foot limits imposed by ASHRAE? Steve, let's go to you.
Yeah, so Jennifer, I think what they're talking about is the refrigerant concentration limits. And so what we have seen with the new refrigerants that are lower GWP are being introduced in the blends, as long as they're non-flammable, the RCLs or the concentration limits are very similar, depending on what the toxicity limit might be. Now, when you move to flammables, obviously we pick up a reduced pounds per cubic feet or RCL value, but then the safety standards take that and really don't use it in the for the equipment design, but in the occupied space, if we're in an equipment room, uses that value. But we really, on the flammable refrigerants, look at the LFL or the lower flammability limit as the concentration, and then there's a safety factor that's added to that as well. So the industry is kind of transforming flammable refrigerants to use concentration limits that are based around a safety factor on the lower flammability limit. And so it's all similar but different, as you would say.
Similar but different. Okay. Let's go to this one. What about R290 use for AC in U.S. with secondary fluid systems?
You want to answer that, Steve?
Yeah, I can take that. So One of the things is if you want to use hydrocarbons in the occupied space, you have to use a very restricted amount, and what that restricts is the amount of cooling capacity you can do. So if the limit today in the United States is 150 grams of refrigerant, you really can only do a small amount of cooling, maybe a window shaker or a small, or I should say a window air conditioner, not a window shaker. I think what they'll think of their shakers, or a small dehumidification unit. But if you move the refrigerant outside and you make a small water-cooled chiller, we can up the amount of refrigerant, up the cooling capacity, and then we have to bring a secondary fluid into the house. And so large buildings do this every day with refrigerants and chillers, but tomorrow do it on residential. If we don't have a really good solution that we are required, yeah, you could do that, but they're probably going to be a cheaper solution, less complex than to try to do all that complication.
Right, and then I guess if you add a secondary loop to your system, that probably negatively impacts your efficiency. So when the efficiency requirements are very tight, it's probably not a good idea, or I don't think it can compete against single refrigerant loops, right?
Yeah, it's less efficient. You lose about 6 to 10% based on the amount of heat transfer and pressure drop you have to take as well.
Regarding the flammability issue, can you comment briefly on the design and cost impact for the typical mechanical system? Roughly what % impact in first cost? Doug, you want to take this one for us?
That's a very good question.
Okay.
We'll see. The product safety standards have not been set for the U.S. market. Internationally, I mentioned in my section on flammable refrigerants that charge limits are very important, so there would not be any additional cost if you're under those charge limits. When we talk about adding leak detection, additional ventilation, shutoff valves, then you get into your added costs for compliance with the installation codes and the product safety standards. Percentage-wise, it's really hard to determine what those costs might be. You have a hotel which might have several hundred different indoor units being utilized versus a larger package system which would just have to have one set of mitigation controls. So that's a very open question, but I don't want to put a % on that, but it does add cost.
But those are the things you need to be looking at. All right, for low GWP, low atmospheric life HFOs, are there breakdown products GWP considered?
Absolutely. So that is part of the calculation. So if you look from cradle to grave, as the molecule breaks down the atmosphere, the pure material you're starting with may not be the thing that contributes all the GWP. It might actually be something that's breaking down in the atmosphere as it eliminates itself from the atmosphere. So that's all accounted for in the value, but it's all brought back to the base molecule.
Okay. Does expanding the use of ammonia present an opportunity in the future to reduce GWP? Is the toxicity and flammability of ammonia too high of a risk to make it a viable refrigerant for increased use in the marketplace?
Yeah, so I think ammonia is getting some increased attention again as we're trying to get to lower GWPs. I mean, ammonia has been used successfully for 150 years as one of the first molecules identified to use in the refrigeration cycle because it was something that man created early and get it out of an industrial process. Now as we move forward and we have different applications and the things are changing, we may see increased use of ammonia, but it's already well established in the large commercial refrigeration markets, in industrial refrigeration, and so I think it's going to hold there. We're going to expand more. Moving into the other applications, you can see new products developing, whether they take a foothold or not. I think the resistance around toxicity is the main issue, and the ability to have a sophisticated service personnel to be able to handle that. But people are considering all kinds of new things in this transition. So,
what is it about the flammable refrigerants that make them have a lower GWP? Sarah, you want to do this one?
Yeah, so if you look at your HFCs, for example, 125, which is a 50% component of 410A, it's actually a very good flame suppressant, whereas R32, which is the other 50% in 410A, it's a flammable refrigerant. And oftentimes a good indicator is you look at the fluorine and the hydrogen ratio, and if you have more fluorines, it tends to be non-flammable, and if you have a higher hydrogen ratio, it leads to being a flammable component. And so if you have a bulkier, heavier component, it's harder to break down and ignite. So Typically, like lighter materials like R32, they tend to be flammable, and I guess.
Yeah, and so, you know, in the
GWP
atmosphere,
aspect,
when you have the molecules that have, one of the things you can design in a molecule is put more hydrogens on it. So propane has no fluorines or chlorines on it, has a very low atmospheric or low GWP because the hydrogens can react in the atmosphere. And so as you add fluorines, they become more stable, like Sarah said, and then pretty soon the atmospheric chemistry, which is very reactive around us, you just don't realize it, cannot break those molecules down. It just takes years and years and years. I can't remember what the half-life of 125 is. It's about like 35 years. So it takes a long time to get half of it gone.
Wow, okay. Next question. Do the changes in refrigerants driven by the Kigali Agreement mean ultimately there's a limited future for air-cooled based as opposed to water-cooled VRF type systems?
Yes, so the big issue is charge.
Okay.
How much refrigerant's used in a system and the refrigerant concentration limit in the indoor spaces. So water-sourced equipment does have a lower charge than air-sourced, and as we move to lower GWP refrigerants, which as we mentioned most likely will be flammable, and you've got to decrease your charge limit and you've got to decrease your refrigerant concentration limit in the space. So we'll see maybe a movement towards more smaller systems than large distributed VRF systems where you've got one outdoor unit with up to 50 or 60 indoor units. You may see more smaller sized outdoor units serving that same space. We may also move toward VRF type systems that have a refrigerant to water heat exchanger. So you've got water going to the indoor units rather than refrigerant, which would completely eliminate your flammability risk for that indoor space. And we'll see larger use of chillers.
Okay. In the 90s, there was a measure, TIWI, that attempted to balance direct and indirect effects of refrigerant. Is there something similar available today?
Yes, there is. TIWI is total equivalent warming impact, and so it measures the, it expresses the value of the indirect emissions versus direct emissions from the refrigerant, indirect being from the energy use. Now the new measure is life cycle climate performance, or LCCP, which includes TIWI, but it also includes a number of other things, like the manufacturing of the refrigerant, the manufacturing of the equipment, what it takes for greenhouse gases there, leaks, which is part of the TIWI, but then the end of the life and reclaim and recycle. So life cycle climate performance is the new measure, which TIWI is just a large piece of it all as well. But it's a more complete picture from a sustainability standpoint.
It's more like a cradle to grave, the whole picture.
The whole picture.
Okay. All right. Are there special lubricant requirements for R454B and other replacement refrigerants?
Well, this is an interesting question. Okay. You know, I mentioned in my talk that I say something about special lubricant requirements for 454B. And then that includes R32 as well. You have to have different refrigerants. And this gets back to the comment I made, all the same but different.
Right.
So we have to optimize the lubricants. So a lot of lubricants we use are POEs, so the industry is used to that acronym, and PVEs. I think the manufacturers are adjusting their chemistries to allow for good viscosity, which is important to the OEMs, and getting the right solubility. And so we're getting there. So we're going to use the same but different.
Again, same but different.
Yeah, right.
Okay. That's your thing today. Yep. All right, next question. What does HFO stand for, and how is it different from an HFC? And I know, Sarah, this came up in one of your presentations.
Yes, so HFO is hydrofluoroolefin, and so if you look at your hydrofluorocarbon, HFCs, you have carbons and then hydrogens and fluorines, and it's a saturated molecule, we call it. HFO is an unsaturated molecule, and it has a unsaturated double bond between the carbon molecules. And so it kind of adds to the instability in the atmosphere, which leads to the lower GWP aspect of these HFO molecules.
Okay. Let's see. Can you assist me in better understanding A2L refrigerants and the flammability of the product and safe handling protocol? Also, when the A2L does burn, do we know if the off gases are harmful, and would you feel comfortable using this product in a system designed for human comfort? me go.
Doug.
Doug, you
I
want to
can
do
take
this
that.
one? Okay.
So the A2L classification was developed as a subclassification of Class 2, primarily to differentiate certain refrigerants from the higher flammability within that class, Class 2. So there are certain number of refrigerants with what's called a lower burning velocity. So the burning velocity test was developed to differentiate between the Class 2 and Class 2L. And Sarah can talk to the specifics of that test, but it was there because certain refrigerants like R32 have lower flame spread, lower minimum ignition energy, and we can see that application of those refrigerants would be easier in direct systems because they are not as flammable as the Class 2 or the Class 3, the hydrocarbon refrigerants.
Yeah, so this burning velocity factor that Doug mentioned, it's indicator of how fast does a flammable refrigerant propagate. So it adds to, there's a cap of 10 centimeters per second to be classified an A2L refrigerant. But most importantly, if you have a lower burning velocity, it means it has a correlation with another parameter called minimum ignition energy. And so it's the energy you need to ignite the refrigerant. And if you have a lower burning velocity, you typically have a much higher minimum ignition energy. So it slowly propagates, but it's also very harder, more difficult to ignite. So there was a study where there was a hair dryer being operated, and they pulled the plug and there was a spark generated by that. So a typical A2L refrigerant would not be ignited by that, but A3 refrigerant hydrocarbons can ignite from that. So it's a additional added safety feature.
Okay. Very interesting. All right, next question. Given the variety of emerging refrigerants and the changing regulatory requirements for refrigerants, what provisions are being implemented to ensure that the various refrigerant blends for installed equipment are available to the technician to service the air conditioning unit throughout its life cycle?
Yeah, so I think what provisions are being implemented to ensure this. As we phase down, just like we're transitioning from R22 in the United States, we're finally finishing that. Refrigerant supplies are becoming less and less. You expect that in the future too. So at some point, we may or may not have enough to service the existing fleet that might be out there that was put out 10 years prior to where we're phasing down. But I think as we balance the gases and as we implement, we should have that, as we phase down a refrigerant, have enough from reclaim and recycle, which is a really important factor that people should be doing every day. Reclaim and recycle the refrigerants that can be reused and reblended back to something we can use in the future.
Okay. Propane use for residential and commercial heating is well established and very safe. Does this give reassurance in using propane as a viable refrigerant?
Yeah, I hate to jump in here.
No,
but
please.
So, propane makes a great grilling gas, right? That's how
Right.
I got to refer to, or a great gas to cook with, right? So, or great gas to heat with, right? But that you're using it directly for a purpose, and we have experience with that, but the amount of charge that's in the house is very small, right?
Okay.
Essentially. And then, of course, in a furnace, it's contained, and there's safety protocols and safety procedures for all that. So now if you're going to put it in a piece of HVAC equipment, and let's say you have a charge of like a pound, let's say, if a line breaks in the house, you have a leak, a pound comes into the house, which is a large quantity in a small area, which can lead to a rather sizable event. Now, it's not uncommon, people see on TV all the time, there's this house that's just blowing up and obliterated by by methane, natural gas. Well, that occurs all the time, right? So there's that safety factor there, what we're used to having. Living up north myself, I need hydrocarbons to keep my house warm. There's no other choice, and I use a lot of them. So it's an important use permit as we do it, but it depends. I think it is safe. It's how you use it.
Okay.
Just
There was
like anything
actually a
else.
story on the news this morning about a house exploding from the natural gas.
Yeah,
Yeah,
it
I
happens.
just saw it this morning. Did you guys want to add anything to that?
I can add something to
Yeah.
that. So, if you look at the ASHRAE 34 refrigerant classification, there's different tiers of flammability classifications. There's 2L, 2, and 3, and there are different criteria and how we define them. And so, Class 3 refrigerants, you need fuel or refrigerant to ignite it compared to the two well classifications. You need much less energy to ignite it, but it also, it's a very exothermic heat of combustion reaction. So for that reason, there's charge limits and product safety codes like Doug mentioned. So I guess, depending on the application and the charge limit, I think the usage of A3 could be restrictive rather.
Okay. Let's see. In the current market, there is a lot of R22 being reclaimed for reuse. Do you anticipate a reclaim market for R410A as well with these replacement refrigerants?
Absolutely. I mean, I think you're just, as we phase out good practice, reclaim and recycle, that market will develop. People will have 410A from reclaimed and recycled and reused. And this, as we do transitions before, we still have R22 around, we still have R12 around, even though it's not in use very much at all. But there's we'll have a large, sizable stock until, the right timing occurs with the phase out.
Okay. Do you evaluate different refrigerants for total GWP impact, including the direct impact and the indirect impact, energy use over the life of the equipment?
I think when you're looking at areas where you don't have minimum efficiency standards, we do a lot of that because you don't have a goal on the indirect side. And so you got to look at, well, what's the trade-off, how much fuel I'm using to run that, or how much electricity. But when you have the manufacturers all have a minimum they hit to, they end up really with about the same looking designed equipment, because there's only one way to get there once you have that. But so when you're in these other marketplaces, you kind of play that off a little bit for consumers, and usually the lowest cost, highest efficiency wins in a marketplace.
Okay, we have time for a quick question. What are some of the drawbacks of R440B that are holding back its implementation versus R32 or R454B? Can that be answered quickly?
Yes.
Okay.
It was one of the refrigerants that I mentioned, like R22, like below 300 GWP. So I think it has to do with the timing, because the industry is now thinking about moving away from R410A, and there's a little unclear in the future direction. Are we going to go back to R22-like capacity, or is there room for new refrigerants in the marketplace? And so it's an active research area, and so there might be new refrigerants coming in the marketplace, so that's what's holding it back.
All right. Well, unfortunately, we are out of time for more questions. I want to thank our viewing audience for their participation today. Before we go, we're going to turn things over to Steve for a summary of today's program. Steve?
Thanks, Jennifer. This brings us to the end of the webinar, and I hope your time with us has been well spent. Myself, Doug, and Sarah enjoyed spending time with you examining the world's most prolific air conditioning system configurations and how those systems will adapt to the worldwide regulatory restrictions and corresponding advancements in refrigerant technology. The global HVAC industry is in the early stages of restricting the production and use of R410A. Today we examine the regulations around HFC phase-down timing, which will dictate the new products and when they will be introduced, the safety and performance of potential alternatives, and the impacts that these new alternatives may have to the design of the equipment, supply, and service streams. On behalf of my fellow panelists, I want to thank you for your participation in this very important program. Jennifer?
Thanks, Steve. And thank you to our panel, Sarah and Doug. Unfortunately, that is all the time we have for today. Once again, I'd like to thank our sponsors, Arkema and Mitsubishi Electric, for their support of this broadcast. Finally, on behalf of ASHRAE, I want to thank all of our presenters and viewing audience for their participation in making today's program a success. Thank you for watching ASHRAE's webcast, The Future of Refrigerants in Unitary and VRF Systems. For ASHRAE and our members worldwide, I'm Jennifer Gladstone.